How do control loops stabilize DC-DC converter design? Imagine trying to keep a boat steady on choppy water. The waves push and pull, but you constantly make small adjustments to stay balanced. That's similar to what control loops do in DC-DC converters. They keep the output voltage steady even when input power or load conditions change. In a DC-DC converter, the main goal is to convert direct current from one voltage level to another efficiently. But the challenge is that input voltage can fluctuate, and loads can suddenly demand more power. Without control, the output voltage could swing wildly, causing problems for sensitive electronics. That's where control loops come in. They work like a vigilant navigator, constantly checking the output voltage and making tiny adjustments to keep it just right. The process starts with sensing the output voltage. This voltage is compared to a fixed reference voltage, which acts as the target. If the output is too high or too low, an error signal is generated. This signal is then amplified by an error amplifier. The amplified error guides the pulse with modulator, which controls how long the switch inside the converter stays on during each cycle. If the output voltage rises above the target, the control system reduces the duty cycle, making the switch turn on for less time. This lowers the output voltage. If it drops below, the duty cycle increases, raising the voltage back to the desired level. This feedback loop creates a negative feedback system. It constantly pushes the system toward the target voltage, correcting deviations quickly. To keep the system stable, engineers design compensation networks that shape the frequency response. These networks adjust the gain and phase of the control loop, ensuring it responds fast enough without oscillating or overshooting. The goal is to have a phase margin of about 45 to 70 degrees, which means the system reacts swiftly but remains stable. Sometimes, a current control loop is added. It monitors the current flowing through the inductor or the load. If the current gets too high, the control system reduces the duty cycle to prevent damage and improve response times. This additional layer helps the converter handle sudden changes in load or input voltage more smoothly. In real-world applications like renewable energy systems or battery chargers, control loops are essential. They keep the voltage stable, minimize noise, and help the system recover quickly after sudden load changes. Properly designed control loops ensure the converter operates reliably, efficiently, and safely. They are the unseen heroes that keep power systems working smoothly, regardless of what the environment throws at them.